Good morning, everyone, and welcome to another Triangular Talk session. My name is Shreya Kalyan, and I'm the CEO of Agora Math Circle. I hope you guys had a great summer. School's starting up again, so I hope y'all have a great year with that. With that in mind, our fall 2022 session will also begin soon, so I can't wait to see y'all over Zoom again. Anyways, back to today's Triangular Talks. Triangular Talks is a forum for students to interact with and hear directly from industry executives across various companies and organizations about how they use STEM concepts and problem-solving skills in their day-to-day work lives. Triangular Talks will be a series of 1-hour online Zoom sessions consisting of 3 parts: an introduction, a presentation, and a Q&A session. These talks will revolve around one central idea: the triangular method for solving problems. This method begins with a problem, and from that one gets innovation, which one will finally use to solve the problem. To help students connect the dots between classes and real life, speakers will be asked what they do every day and how they apply their knowledge of STEM and problem solving. This will introduce students to different industries and motivate them to nurture their problem solving skills and not give up. Most common question asked by my students or in any math class is, why are we learning this, or when will we ever use this? This program will answer these questions and encourage students to take the initiative to learn and do more. Today, we are joined by Mr. Rahul Narayan, a principal data scientist at Nike. He has received both a master's in biomedical engineering and computer science and engineering from the University of Connecticut. He works in the machine learning domain and has worked on topics regarding speech recognition, fraud detection, and search algorithms. Currently, he is a biomedical engineering doctoral candidate at Oregon Health and Science University. There, he is conducting research on designing and translating novel medical devices and systems for use by patients, particularly those with type 1 diabetes. With that, the floor is yours. Thank you for joining us today.
All right. Thank you, Shreya. I'll get right to it. Okay, good morning, everyone, or good afternoon, wherever if you're on the East Coast. So I'm going to be talking about my research that I'm doing at OHSU, which is hybrid machine learning ODE models for type 1 diabetes. So this is how I have broken down the presentation. I'll give an intro, my personal intro, and a little bit of intro into biomedical engineering. Then we'll delve into the problem, which is the unreasonable math of type 1 diabetes. Then going by the triangular framework, the next step is innovation. So there are 2 innovations here. One is the hybrid ODE ML model for prediction of glucose response after a meal. And the other one is the ideal meal image generation using DALI 2. And all these innovations are packaged in a solution where you're able to estimate macronutrients of meal from images. And I'll talk about next steps in the last slide. Yeah, feel free to shoot away any questions in chat and I'll be answering them at the end. A little bit of personal intro. I got my bachelor's in computer science from India, and I came to US to do biomedical engineering. So I have a master's in biomedical engineering and computer science engineering from UConn. For my master's thesis at UConn, for biomedical engineering, I did high order statistics of natural and man-made sounds. So this is how you try to differentiate natural and man-made sounds through just sound statistics. And for my master's thesis in computer science engineering, I worked on efficient techniques and algorithms for location-safe smart devices. So these are devices where you fit GPS sensors on them, so you can actually sense the location of devices and actually lock them. And currently, I'm a PhD candidate at OHSU. I work in the AI for Medical Systems Lab. Our lab primarily researches AI for type 1 diabetes, but we are also getting into type 2 diabetes. I also have a work life. I've been working in the machine learning field for around 10 years now. I started out at Aetna, which is a health insurance company. Then I moved on to Amazon. I worked in different teams at Amazon, including Alexa and fraud detection team. And currently, I'm at Nike. I'm a principal data scientist at Nike, and our team powers the search algorithms that you can see on Nike.com and Nike app. In terms of interests, academic and others, I'm a vegan, so I'm involved in animal rights. I like robotics. I like cats, mainly like big fluffy cats like Maine Coon and Norwegian Forest. And I also love teaching. My academic interests include fairness in AI, um, reproducibility of research. A lot of research these days, you're not able to reproduce because people don't share code and data. And that kind of puts a question into like validity of the research. So there are few organizations that are really pushing to make sure code and data is produced along with the research. In terms of biomedical engineering, so I started out as a computer science engineering, but biomedical engineering like fascinated me. So what is biomedical engineering? There are many ways to explain biomedical engineering. Some of them are like engineering sciences plus biomedical sciences plus clinical practices, biomedical engineering. An easier one would be engineering plus biology plus medicine is biomedical engineering. Or you can say it's designing and solving problems of engineering and medical and biological sciences. That's biomedical engineering. All in all, it's using engineering technology for the solution of medical problems. That's biomedical engineering. For me, having been able to apply engineering in the field of medicine gives me like my job a meaningful purpose, and that's one of the reasons I chose biomedical engineering. There are many applications of biomedical engineering. The applications are almost endless, and it develops every day. Like you can build cardiac monitors to clinical computers. Like you can build artificial hearts to contact lenses, wheelchairs to artificial tendons, modeling dialysis therapy to modeling the cardiovascular system. Something I've noticed is that when I was at UConn, a lot of pre-med students actually took biomedical engineering as their pre-med degree. So yeah. So what is the problem we are talking about here? So it's mainly disease management with type 1 diabetes. Over 500 million people in the world currently live with diabetes, and there are two types of diabetes. One is type 1. Type 1 is the genetic kind. It's an autoimmune disease. It's not related to diet or exercise. Here, the body does not produce enough insulin. Instead, the person has to take insulin to live. And then you have the type 2 diabetes, which is influenced by diet, exercise, and genetics. The body can create insulin, but does not use the insulin properly. Type 2 diabetes can be managed through diet, exercise, oral medication, and insulin. Whereas type 1, it's not curable. It's all about disease management, and the person has to take insulin to live. Before insulin was actually could be administered externally, type 1 diabetes was pretty much a death sentence. You only live up to you're like 20 years old. And it's very unfair disease because you get it like genetically. And currently, like almost it's predicted that like it's estimated that almost 1 out of 3 people would have any kind of diabetes in the future. So it's turning out in it's becoming like an epidemic here, not just in the US, but in the world as well. So what is insulin? Insulin is a hormone produced in the pancreas. It's a very important hormone because it allows our cells to use glucose. Without it, our body cannot create energy. And so if people who do not produce insulin, they have to either inject insulin, or you have pumps which automatically once you enter in it, it'll actually like keep pumping in insulin to your body. Here comes the unreasonable math of type 1 diabetes. What we take for granted, or what people without diabetes take for granted, for example, just living normally is hard for type 1 diabetes patients, which mostly kids are diagnosed, especially like at the age of around 6. They have to like estimate, they have to plan out their meals. And after planning out their meals, they have to figure out the amount of carbs in each of their meal and then estimate the amount of insulin that's required and inject insulin half an hour before the meal. A lot of people like don't even bother to do it half an hour before the meal. They'll do it like right before the meal because they forget to take it. So you have to plan your life all like pretty much every single day. And you feel like you're playing a video game where you're like oscillating between high blood sugar and low blood sugar. If you take too much insulin, it's low blood sugar. And if you don't take enough insulin, it's high blood sugar. So it's a very precarious line between the two dangerous states here. I think this tweet pretty much sums it all up. Insulin is extremely wild because too much will kill you and not enough will kill you. And when you're like, wait, what's the right amount? Your body is like, it's a secret. And our lab's objective is to make disease management for patients with type 1 diabetes easier so that they don't have to think about estimating the carbs in their meals. They don't have to think about entering the carb values, or they don't have to think about like how much of insulin they have to put into the body. It's like so that everything is automated. All they have to do is like have a sensor and a pump attached to the body, and the algorithm and the system would take care of it. Innovation. In terms of PhD research, you always start with a hypothesis, and hypothesis could be anything that the sky is red, and then you observe and take pictures and then figure out, okay, our hypothesis was proven wrong because sky is actually blue. So in my case, the hypothesis is that proteins and fats also affect your blood sugar level. Traditionally, the entire research in type 1 diabetes or type 2 diabetes is centered around carbs. Say like if you take more carbs, you need like more insulin. But we are saying that, or we are hypothesizing that proteins, fats, fiber, caffeine, and other like nutrients actually affect glucose response. So that's the hypothesis. And to test the hypothesis, you obviously need, actually, let me go to the next slide. So you need a study design. So our lab does clinical trials because it's a medical school. So there's always an inclusion and exclusion criteria for the study. The inclusion would be like age between 15 to 71 years, and they should have had a clinical diagnosis of autoimmune type 1 diabetes with a duration of greater than 2 years. Exclusion criteria would be pregnancy, other kind of diseases like hypertension, chronic kidney disease, or stage 3 or worse. So almost 24 patients were asked to complete 150 total minutes of exercise per week during the 4-week protocol. They were given sensors. They were given a cell phone with the T1 Dexy app. So with the cell phone, what they do is, they are supposed to take images of all the meals they took during the 4-week protocol. And these meal images are actually sent to the cloud, and it'll be analyzed by nutritionists to estimate the nutrient content. So this is how the data for the study is collected. Now going back to the previous slide, I got the order mixed up. So the question is macronutrient information useful for predicting postprandial glucose? Postprandial means like after food. So now you have this data set that is collected from the study, and you would have the total nutritionist from the image. It'll actually calculate the meal size, the amount of protein, fat, carbs, alcohol, caffeine, sugars, fiber, and water. And also you'll know how the amount of exercise they have done. And so this is the data that's going to be fed into the machine learning model and also the mathematical model to predict response. And this is the response that you're predicting. So glucose response would be like, glucose response is a curve. So you want to find the area under the curve. Area under the curve is not a good measure because area under the curve would always be like high after a meal. But you want to find the incremental area under the curve. That means from the starting glucose, for how much did the area increase of the curve. So that's the prediction. So you're predicting the incremental area under the curve using all these features, and it's feeding this data and using an algorithm and getting to the model. There are two different worlds of modeling. One is the machine learning model where you feed data. The data would contain usually the features and labels, but there are also machine learning methods where you don't need labels. That's called unsupervised machine learning. But traditionally, like most of the modeling is supervised, and that's what we have done here as well. But then you also have mathematical model. You can explain any phenomena with an equation. The equation might be very complex. So and usually like differential equations are used in order to express such models, because simple linear equations would not be enough to explain complex systems. And partial differential equations and ordinary differential equations are used across many applicative areas. I know like most of you are high school students and so middle school students, like, so bear with me, you learned this in high school. A differential equation is an equation involving one or more derivatives of an unknown function. And the order of a differential equation is the order of the highest derivative that it contains. So in this table on the right, the highest derivative in the last, this equation is d square y by dx square. So the order is 2 and it's a second derivative. An ordinary differential equation means it's a full derivative and not a partial derivative. And ordinary differential equations, they have solutions just like any algebraic or mathematical equation. ODE is an equation involving function of one variable and its derivatives. So examples of ODE would be like y derivative plus y equal to 0, or dx by dt by x squared t is equal to sine t, or y double derivative is x cos y. The difference is that for algebraic equations like x squared is equal to 3 and x power 6 plus 7 is equal to 5, where the solutions are numbers, the solution of an ordinary differential equation is a function that satisfies the equation. So that's the tricky part here. Here is an example. So in this case, this is the differential equation, and by this function, e power minus x is a solution, because if you have the derivative of e power minus x is minus e power minus x. So if you add these together, you will get a 0. So, and ODEs can have many solutions. 2 to the power 2 e power minus x is also a solution of this ODE. So this is how ordinary differential equations are solved. In terms of methods, it's a bit involved here. So you start with the human who took part in the study. You create a digital twin of human. This is so you create a digital twin, a virtual human using insulin sensitivity, weight, height, total daily insulin requirement. And once you get this digital twin, you do multiple simulations and figure out the glucose response for each of these simulations. It's the reason why you're using a virtual twin is for humans, we'll have to do a very long study to try out different type of meals or different type of exercise and see the response. So whereas for a virtual human, it's easy to simulate and see responses pretty fast. And then once you have this data set, you use a model. In this case, I used a random forest model. That's the machine learning model. Machine learning models are usually, one of the negatives of machine learning models is that even though they give really good predictions, it's really hard to know what happens inside it. So I use another library called SHAP, which will actually tell you what actually happens with the machine learning model. In terms of the mathematical model that I was talking about previously, mathematical models are easily understandable in the sense that you know what's happening, unlike machine learning models. But the prediction accuracy of mathematical models are slightly on the lower side. So, but we want to get the best of both worlds, especially in the medical field. Clinicians and physicians, in this case, endocrinologists, they want to know what actually happens with a model, because some of these are life and death situations. If your glucose level, if your blood sugar level goes really down, you die. So they want to know like what actually happens with the model. You just don't want a black box model. So we decided to combine ODE models with machine learning models, and not just regular machine learning models, like explainable machine learning models, so that the entire process is it's clear and evident what happens inside the machine learning model. So going back again, you build a virtual human from a human, and then simulate a lot of CGM responses, which is continuous glucose monitoring responses, and then build a model to figure out what factors affected this glucose response. You're trying to predict this glucose response. You're trying to see if, let's say, if the carb is 50 grams, how would the glucose response change? If you add proteins and fats, would the glucose response be lower or would it be higher? So you're trying to figure out all the scenario and figure out if macronutrients actually affect glucose response. So these are the results from the study. So the study data is very huge. These are preliminary results from a pilot data. So this is not publishable. So you want the full data set before publishing, and full data set, they said it's going to come in October. But these are the preliminary results. And this plot is pretty involved, so bear with me while I explain how to read this. So these are the features that went into the model, like proteins, fats, carbs, fiber, etc. And these are feature values. So blue means low feature value and high means high feature value. And on the x-axis, you have SHAP values. So anything that's to the right of 0 means it's affecting glucose positively. So, and anything to the left means it's affecting blood sugar like negatively. To give you an example, carbs, it's red to the 0. Red means high. So high value of carbs increases glucose since it's to the right of 0, which is already known. But with the study, something else that came out is that protein is red and to the left of 0. That means high value of protein decreases glucose response. With fat, similar behavior, it's red and to the left of 0. So high value of fat decreases glucose response. Something interesting that came out is caffeine. It's red and to the right. So high value of caffeine actually increases glucose response. And this was very interesting. Like you just have coffee and it says that your glucose response when goes up. Our clinicians said that they had like few patients that tell them all they had was a coffee and their blood sugar rose up. So it's, yeah, there are a few anecdotes of this happening, but this is a very new finding. So now these results kind of tell us that we need to not just look at carbs, we also have to look at other nutrients, proteins, fats, and also caffeine, water intake, fiber, to figure out what the glucose response is, not just because carbs don't give you the full picture. So that's the summary result from the study. What's the solution? So once we've realized, okay, it's important to not just know what the carb amount is in the meal, but you also want to know what the proteins and fats are. You can't have users just estimate. It's very hard for users to even enter carbs, and it's going to be harder for them to think about proteins, caffeine, fiber, and other nutrients as well. So the solution is to build an app. So this app uses a machine learning model known as convolutional neural networks. And once you take an image, just based on the image, it's able to estimate the nutrient content in the meals. So in this case, it's beans, there's an omelette, and potatoes. And all you have to do is take a picture of your meal, and the app will spit out the breakdown of your macronutrient information. Right now, there are apps like MyFitnessPal, but those are more like databases where you enter your meal and it'll check from the database what the macronutrient breakup is. Here, all you need is take an image of the meal and it'll give you the macronutrient information. This is a really tough problem. We have been iterating our algorithm to get better accuracy, but we are having challenges with food items like, let's say, soup or curry, where it's all mixed together and it's an even color, so you never know what's inside it. So there are a few challenges, but we've been getting like decent accuracy as well. So how does all of this integrate? So you'll have a smartphone which you can take pictures of the meal. Then obviously you have the insulin pump, and then you have a CGM sensor. So CGM sensor just measures the glucose response after monitors the glucose in your body. So like if it's going high, it'll sense, okay, glucose is going high, this person needs insulin, and it automatically sends signal to the insulin pump, and the pump would dispose of insulin. And you need a cloud monitoring tool. So this is where all the data would be on Amazon Web Services. And if you want to also track exercise, you can use a fitness watch, which can be integrated to the system. Exercise is tricky because in our lab, we have done studies on exercise, and we have shown that aerobic exercises actually decrease your glucose. So if you do a lot of aerobic exercise and you have diabetes, there is a chance you would go into hypoglycemia, which is lower blood sugar. And again, it's dangerous. Whereas resistance exercise, it looks like from the studies in the lab, resistance exercise kind of maintains your blood glucose level. This is because your body also produces glucose. So the glucose that you lose during exercise is made up by the production during resistance exercise. So it kind of maintains the glucose level. So resistance exercise is recommended unless you're planning to take a rescue carb during the exercise. All right, so this is one of the solutions that we are looking at, to have a fully closed loop artificial pancreas. Pancreas is a hormone that releases insulin, so we call it iPancreas. Okay. Something else we are also looking at is to what is ideal meal generation using DALI 2. So DALI 2 is a new AI system that can create realistic images and art from a description of natural language. So all you have to do is enter a text prompt. So you just say a photo of an astronaut riding a horse, and it'll actually give you a photo of an astronaut riding a horse. And something important to note is that this image never existed in history. It's a totally new image that was generated by AI. And then let's say this one is a good example, a medieval painting of Wi-Fi not working. And this one is olive oil and vinegar drizzled on a plate in the shape of the solar system. So you have this. And again, to note, like, these images have never been generated before. It's like newly generated images. What we want DALL-E to do is we give different text prompts and create different combination of meals. And these meals would go into our carb estimation, macronutrient estimation app. And once you get all the macronutrient content, we will simulate glucose response using the simulator in our virtual humans and see if there are meals that are like ideal for diabetes patients. So that's the idea here. We had some fun with DALL-E. DALL-E 2 was developed by OpenAI, and if you want to try out DALL-E 2, you can sign up with them, and they put you on a wait list, and you'll get it like within. I think I got it in 2 months. The wait list might be smaller now, but you never know. So you tried Spider-Man Nike shoes. It actually comes up with Spider-Man themed Nike shoes, right? Nike Ferrari shoes. That was the text prompt, and it actually generated Ferrari themed Nike shoes. DALL-E is a portmanteau of WALL-E, which is a movie, and Salvador Dali was a surrealistic artist of the 20th century. How does DALL-E work? So let's say it starts with a text prompt and creates an image. So a corgi playing a flame-throwing trumpet, and it creates this image. So what happens in between? So you have this text prompt. This text prompt is converted into a text encoding. When I say text on encoding, think of it like a huge vector of numbers which contains meaning of these words. It's like you are just like binary numbers, how you convert language into binary numbers. This is converting text into numbers, in this case, vector. And this another, in the second step, a model called prior maps that text vector, text encoding into an image encoding. Again, here the image encoding is still a number, a vector, a huge vector with numbers. And I pretty much, I think all of you know that an image is made up of pixels, and each pixel has an RGB value, red, green, blue, like value numbers, which defines an image. So this maps text encoding into an image encoding, and finally an image decoder. So now you don't have an image, it's just a vector of numbers. An image decoder stochastically generates an image, which is the visual manifestation of the semantic information. So this is how the entire pipeline works. But there is, but you also want to know, how is this model able to convert a text encoding into an image encoding? This seems to be a tough task. How do you understand the meaning of these words and convert this into an image? So that I'll explain in the next slide. DALL-E 2 actually contains two models. One is the CLIP, contrastive language image pre-training model, and the other one is the diffusion model. CLIP has been trained on almost 400 images with titles in it. So let's start with this image. It's the title of the image is Pepper the Aussie pup. So you take the image and its title, you differentiate it, and you put the title through the text encoder and the image into an image encoder. So what you do is, you know Pepper the Aussie pup is the right title for this image. So this image would go on the first cell. And so your first row would be the image, which is this image. And the right title would be the corresponding column. So along the diagonal, so you have 400 million images. So along the diagonals, you have the right combination of image and titles. And the other cells are filled up with mismatches. So you have this title with, let's say, this is an image of a car. That is wrong title would be this. So or it'll be this. So you'll have like entire cells filled with wrong titles or mismatched title and images. And along the diagonal, you have the right title and image. So this model, this data is fed into the model, and this model learns, it's contrastive learning. So it learns to figure out the right title and right image and differentiates it from all the mismatched images and title. So it's just like humans. It's learning from good examples and learning to differentiate good examples from bad examples. So if you have both good examples and learn bad examples, you're able to learn more. But the model is able to learn at scale here. It's 400 million images. So this is how it knows how to convert a text into an image, because it has already learned what the right title for almost 400 million images are. So it knows, it's identifying all the patterns, the sentences and images. So that's CLIP. And now you have the diffusion model. So this step creates an image encoder. This is just a vector of numbers. It doesn't create the image. But now you need the diffusion model. Diffusion model it's actually comes from electrical and mechanical engineering. It's been adopted into machine learning recently. So like I said, all images are made up of pixels. So here you start with an image of random noise. It's like random pixels or random numbers. And you continuously iterate randomly until an image is formed. This requires a lot of iterations, because it's like when you say like you can make a monkey type a Shakespeare a novel, if you make it do 1 billion iterations, it's kind of that. But here you can also guide the process in between, so that the numbers that are mutated can form an image. So diffusion models starts from like random noise and comes to the final image. But this can be leveraged here. So you have these numbers, and you can use a diffusion model from the numbers to generate the image. So this is how the two models work in tandem. Yeah, that's pretty much the solution. In terms of next steps, there's a lot more to be done. The first thing is we figured out, from at least the preliminary results show, that macronutrient inputs are important, and not just carbs. We need all other macronutrients as well, and it improves prediction accuracy. We also showed that not just machine learning, but you can combine machine learning and OD-based physical models to improve prediction accuracy. I haven't gotten the full data set yet. So you want to run the model on the full data set. And then I'm really happy about this aspect. The full data set also has genetic markers. So you can even say what genetic markers are predisposals for like having type 1 diabetes. The image recognition model to extract macronutrient information from images, it's still being built. You need like really good accuracy before you can put it into an artificial pancreas system. And so a closed loop artificial pancreas control system with meal macronutrient detection app is a promising avenue for pre-diabetes and obesity interventions. So here, what we have shown is that it's good for type 1 diabetes, but another promising avenue is pre-diabetes. This is where you have all the indicators that you're going to develop diabetes, and that's the best time for intervention, because it's hard once diabetes is a disease state. So it's hard to manage a disease. Obviously, always prevention is better than cure, right? So so you identify pre-diabetes candidates and put them on a closed loop artificial pancreas system, and it'll actually help them reverse the pre-diabetes, and so that they don't get into the diabetes stage. And any control system, any artificial pancreas control system that needs to that can be commercialized and can be used on patient needs to go through a clinical trial. So we'll have to do a study once we have the system in place to study efficacy and adoption of intervention. So we'll be looking for like volunteers, recruiting volunteers who will be ready, willing to go through a few week study with the system, and then we'll be tracking them from the data that's posted on like AWS. So these are pretty much the next steps. Yeah, it's going to take a few more years of research, and with research, it's very rarely you can come up with a completely new invention or discovery. It's mostly incremental improvements over previous research, and that's how foundation of science is built anyway. Like you don't like come out like with magic right off from blue. It happens once in a million when some like genius comes up, like someone like Newton or Einstein comes up and comes up with all these new inventions. But it's almost always science is built upon incremental research was done on previous research. So that's pretty much what I'm trying to replicate here as well. Thank you all for listening. I can field any questions you have right now.
Thank you so much, Rahul. That was incredibly helpful and insightful. So yeah, the audience, please feel free to unmute and ask your question. Maybe while people are thinking about it, I can get people started. So maybe a more fundamental question, Rahul, is you mentioned that the starting point for this was initially the assumption was that carbs are the only elements that influence glucose levels, and then one of the findings was that no, it's a broader set of macronutrients. And you talked about ordinary differential equations, and then using I don't know if at that point you used machine learning or not, but couldn't the differential equations or like a multivariable regression also have led to that finding, which is that it's not just carbs, but it's also others. I guess maybe I missed the point about was there an element of machine learning that was involved here, and if so, why was machine learning needed, and why couldn't we have done this with like a multivariable regression or something?
Yeah, that's actually a really good question. Yeah, why don't we just use OD or a simple regression? So if what happened is that when you build an OD and predict glucose response, we have response from the study, right? The accuracy was lower than 50%. So when you have a model that's accuracy is below 50%, means it's just like flipping a coin. It could be either high glucose or low glucose. So those systems do not have enough prediction accuracy to take any insights from the results. Whereas machine learning models, you get accuracy around like 70 to 80%. And now you know a model that can actually like predict, and now that gives you confidence in the model. And so then you can come up with all these insights. So that's the reason like you need machine learning model. And in our case, we combined the machine learning model along with the ODE model. So you get an extra. So we got an extra bump of 6% by just using ODE on top of machine learning model. So that's the difference here.
Got it. Thank you. And it seems the other way that you are also using machine learning and AI is that image recognition, and how do you leverage that for the closed loop? Is that fair?
Yes, that's right. Yeah, there are like three, I guess, touch points for machine learning here. One is to make for insights, to make the model explainable and see like what's actually happening. The other one is the image recognition model to estimate macronutrient contents. And the third touch point is DALI, where we're actually creating new meals or meal images.
Got it. Thank you. Any questions from the audience? Feel free to put it in chat or just unmute and ask the question. Yeah, so there's a question on chat, Rahul, if you'd like to take that up.
Okay, can you, so the question is, can you talk about the ML tools and library used for this analysis? So most of our work is done in Python. And libraries, the machine learning libraries used are scikit-learn, PyTorch, and TensorFlow. And we run it on an AWS platform. That's our cloud provider for OHSU. So these are the tool sets that we use. And to fetch data, the data is in S3 and use lightweight SQL to actually get the data. And all the data transformation are done using Pandas library, which is again a Python based.
Rahul, while we wait for more questions, maybe more on what got you interested in biomedical engineering? And I think you gave a really nice intro to biomedical engineering and the definition, etc. So it seems that you did two masters. One is in biomedical engineering, and the other was in computer science. And now you're sort of bringing those together to do a PhD. So really, really curious about what sparked your interest and just your journey.
Yeah. For me, there have been a lot of studies done which tell you what makes you happy at a job. It's not the money, or it's not your salary. At least it's not the first reason. It's not your salary, or it's not perks like free food that Facebook and Google provides, right? A lot of studies have come up and said the major reason for happiness in a job is whether you think that your job has a meaningful purpose. And for me, biomedical engineering, you have your meaningful purpose right there. There are so many medical problems which can be solved by engineering. Type 1 diabetes is one reason, cancer is another, like obesity. We have an obesity epidemic, that's another. So there are, and that makes me happy to work on a meaningful, like a job with a meaningful purpose. So this is my primary attraction to biomedical engineering. And I have relatives with type 1 diabetes. I've seen their struggles. I also have an uncle who's like hard of hearing. So my master's, I got into like speech recognition because I thought like a lot of the technology that they have is very, very rudimentary. So there is a lot of work that can be done. Even right now in medicine and healthcare, engineering and tech is at least 10 years behind. I'm like being generous here if I say it's only 10 years behind tech. It's a lot more, it's far behind. So we need more engineers and scientists in the medical field to at least to bridge that gap.
Got it. Thank you. It's always, not always, but it's nice to hear, what inspired somebody. So thanks for sharing that. That's super helpful. And for students who may be interested in biomedical engineering, what advice would you have, Rahul? Especially with I think machine learning and artificial intelligence, that those buzzwords get thrown about a lot, right? I think people use it very loosely, but it is certainly, an innovation that has permeated into different walks of life, and we certainly want to leverage that even in biomedical to advance. Advance and meet the needs of patients, I guess. So maybe prior to this research, people had considered that, okay, this is how people with type 1 diabetes will live, right? So this is how it's going to be, and people had actually accepted it. Now you're trying to sort of push the boundary on that with some of the newer technologies that have become available. Just curious about your thoughts on how can students prepare themselves to revisit some of the problems, and even if it may be characterized as incremental innovation, it's still important for those patients. So how can students prepare themselves?
Yeah, you're right that AI and machine learning, those are buzzwords that get thrown around a lot. But the way I'd look at it is that data science and machine learning is going to be ubiquitous now, and it's going to be like more in the future. Think of them as just tools in our repertoire, just like your Microsoft Office and Excel to do certain tasks. AI is just going to be a tool, but you really need good, solid math and science foundation. So biomedical engineering, in and a lot of work that I do, you need a lot of electrical and signal processing background because you're dealing with sensors. And so the interesting part would be, I would say, like when you're in high school or middle school, like get started with small projects, small engineering projects, where you're working with. Because we have, you can talk to different labs or universities in your area, and they'll give you like internship. We have high school students doing internships in our lab, and they'll be working on like something like really small project, but you'll be like completely able to get the full entire workflow or how research works. One of the students, high school students in our lab, worked on. So when you inject insulin, he actually has type 1 diabetes. So when you inject insulin, if you keep injecting insulin at the same location, there's a fat buildup, and so you might not get the right amount of insulin all the time. So he worked on looking at a sensor that detects the fat amount in injection sites, so that they know like if the fat amount is really high, you don't use that site. So he worked on a small project. We have actually like our advisor's son who's working on a small app this summer too. So work on like small projects with a medical aim. It could be something very simple, and I think then you will see like whether you're actually interested in biomedical engineering, and have like make sure that you have solid math and science background all through your college. Like I said earlier in the talk, biomedical engineering seems to be like really popular among pre-med students. So apparently it helps them with their it's MCATs, right? Yeah, MCATs too. So that's something to consider. If you have this biomedical bachelor's degree before you go to med school, you become really powerful. You know how the sensors and medical devices work. So you'll actually be able to be a better doctor as well.
That's some really great advice on, just getting connected to local universities and seeing if you can, getting hands-on, and even using that as an opportunity to test whether this is a field for you, or if this is something that you're interested in. So thank you for sharing that. There is another question on chat. Rahul, would you mind taking that in as before, if you could read the question and respond to it?
Yeah, that's so how about the combination of nutrients? Will it influence? Yeah, so here, more than the combination, it's if there's any interaction. So if carbs and fat interact against each other and affect, so you have to look for interactions as well. We haven't included it in the first version of the model, but that's a very valid point. You have to look at like interactions of variables, interactions of macronutrients, or between them, like what is, for example, here caffeine is showing up as increasing glucose. Maybe it's because people are taking sugar with caffeine, right? And this model is telling us that, okay, these are just people having sugar with their coffee, and that's why it's showing that it has high glucose response. So yeah, really good question. We don't look at it here, but it has to be looked at.
It's probably one of your, potential next steps that you might consider in sort of refining your model. Is that something that you would think about?
Yeah, absolutely. Yeah, and the point that you mentioned about local labs, local like university labs are more than willing to take high school students. Like you would be surprised how open they are. There are a lot of labs that are super busy, but you'll be surprised the amount of labs that are open to having high school students come into projects.
That is very encouraging to hear. I think one of the first questions that came to mind for me is, okay, how do we find these labs and how do we approach them? Type of question. But it seems sometimes it's also a numbers game, right? So you reach out and I'm sure there are opportunities out there to grab. So thanks for that that piece of information as well, which is very encouraging. I know we're coming up to the top of the hour. We have 4 minutes. I will maybe pause for 30 seconds or so to see if there is anyone that wants to unmute and ask a question. If not, I'll go ahead and close this out with a summary. But let me pause for a few seconds. It's surprising that only when you pause you realize how long 30 seconds can be, actually. All right. First of all, Rahul, on behalf of Agora Math Circle, I want to express our sincere thanks. And I think, for all of us who heard Rahul's intro, he is not only a full-time, employee at Nike, so he's also a part-time PhD student. So he's very busy, but he has taken time out of his busy schedule to be here with us today. And as we've spoken previously, it's not just showing up for this hour, but there is a lot of preparation that goes into, preparing for the talk and coming here and sharing with us the information. So I really do want to take the opportunity to acknowledge you, Rahul. And I see that you have flashed up the funders and collaborators. Is there anything that you'd like to say at this time with this slide?
Yeah, so I'm not, like, my PhD is funded by Dexcom, so it's one of the producers of CGM sensors. So unlike your master's, PhD is like usually like fully funded. So you don't have to pay for, and you also get a stipend. In my case, since I'm working another job, I don't get the stipend, but I don't have to pay any money towards tuition. So that's something to keep in mind. But research would not be possible without donations from trusts. So we have Hemsley Charitable Trust that was built up, and they give out fundings for various research labs. So there's a lot of moving parts in how a research lab works. So yeah, I would like to thank all my sponsors as well.
Thank you, Rahul, for sharing that. So going back, so I'll do a quick summary. I know we're already a minute away from the top of the hour. So it was really interesting to, first of all, take an existing problem, right? So it's not an unknown problem that, with type 1 diabetes, there is, fluctuations, and people at some point have accepted that, okay, this is how life is going to be. And it's really encouraging to see that, universities are continuing to push the envelope on research and push the envelope on the solutions, right? And with the evolution of technology in the form of machine learning and AI, it seems that you're leveraging that in many ways in this project to be able to get to a better lifestyle for these patients and better disease management. And I think you sort of touched on it. One is, how do you make the algorithm itself better, right? So in terms of what are the predictor variables, etc. So identifying that. And then the part about having the virtual simulator as opposed to having humans, I think that was very interesting. And being able to create that and being able to generate more data through that, and fast, right? So which was interesting to see. And then the DALI part that you talked about, where you have the image recognition, which I thought was pretty cool, right? Where you just take a picture of it and then it uses that to tell you what is the composition of your meal, and hence what is the insulin needed in order to control your blood sugar levels. I think it's a really great way to leverage AI machine learning as a tool to come up with a solution for an existing problem, and pushing the envelope on it. So thanks for sharing this research with us today. And for those of you who've sort of been with us on this triangular talk journey for a while, this is really, really early part of research, right? So it's where we've not gotten into clinical trials. If you remember, we had a talk about how long does it take for research to come to fruition and then to scale the manufacturing and whatnot. So this is a really early part of research. So hopefully you're able to connect the dots, as you're learning and getting new information through these different talks, and you're able to put some of the pieces of the puzzle together for yourself. All right, with that, thank you, Rahul, and thanks everyone for your participation today. I appreciate it. All right, have a great weekend. Bye.
If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!